Hello, can everyone hear me? If you can hear me, can you please raise the hand in the chat, please? Oh yeah, okay. Thank you. We'll just wait for everyone else to join. Yeah. Let's start like in 1 minute. Let's start in 1 minute.
Okay, so let's see if we can. Just so you know, sure it has it there.
Yeah, thank you.
It's charging.
Yeah. Okay, we'll get started now. So hello everyone, my name is Stella, and I'll be taking the chemistry crash course for today. So I think I've I've subbed in for some of you guys like chem class before, but yeah, I'll be taking the crash course for today. So we'll get started. So this one's on module 2. So I think like in the term that you're going to be going into, you'll be starting module 2 if you're like going in order. I think like some schools don't go in order, but hopefully for term 2 you'll be covering module 2 in class. So we'll get started. So this module is like all about like quantities and just quantitative chemistry in general. So the main syllabus areas we're going to be covering today is the chemical reactions. So this includes like balancing equations and our common chemical reactions. So this is like decomposition, synthesis, acid-base reactions, stuff like that. And also we're going to be covering the concept of the mole. So this is if you've heard of like Avogadro's constant, this is what the mole is. So we'll be covering these topic areas for today. Okay. If you have any questions, just pop them in the chat and I'll answer them when I can. Does anyone have any questions so far, or can I get started? Okay, perfect. All right, so we'll get started on balancing equations first. So this part of the syllabus, this is the syllabus dot point right here. So it's asking us to relate stoichiometry to the law of conservation of mass in chemical reactions by investigating balancing chemical equations. So if you guys don't know what stoichiometry is, it's basically when we relate, we're trying to calculate the quantities of reactants and products in a chemical reaction. Okay, and in order to calculate these quantities involved in these reactions, we have to make sure we know the chemical like ratios of the reactants and products. So we do this through balancing our equations. So that's why we have to balance our equations to actually make sure that we can calculate the correct quantities of the reactants and products involved in these reactions. Okay, so I'll just write down a definition here of stoichiometry. So it just this involves the calculation of quantities of reactants and products involved in chemical reactions. So you hear a lot in this module. You hear like stoichiometric ratios and stuff like that, and this is what it's relating to, just like the ways in which the quantities of certain reactants and products they work together. Okay, so we'll start with an overview. So in a chemical reaction, new substances are produced through the breaking of bonds and the formation of new bonds. Okay, so usually chemical changes are difficult to reverse. So they're not always, it's not always impossible to reverse chemical reactions, but for this module, we'll just focus on like reactions that only go in one direction. Okay, so for all chemical reactions, mass is conserved, meaning that atoms are not created nor destroyed. They are simply rearranged. Okay, so this is an important point to remember, that mass is conserved. Okay, so if we start, for example, with like 5 sodium atoms in our reactants, then we'll always end up with 5 sodium atoms in our products. Okay, we'll never lose a certain number of atoms, but they may be in like different forms, like in a different compound, or maybe like it will be like existing on its own, for example. Okay, so we have this little diagram here. So this diagram, it shows us we have 2 of these diatomic molecules. So usually in chemistry, when we represent an atom like as a white atom, it's usually hydrogen. So this is going to be hydrogen gas here, so H2. So we have 2 hydrogens, and then we have, so 2 H2. And the reason I put H2 is because these atoms, they're existing as diatomic molecules. So there's 2 of them in one molecule, okay? That's why I put H and then the subscript of 2. And since there's 2 of them, like 1 and 2, that's why I put the coefficient of 2 here, okay? And then it's reacting with these 2 larger red atoms, and usually we represent oxygen as these red atoms. So this is going to be oxygen, okay? And there's only so there's 2 of them together, so that's going to be O2, and that's reacting to form 2 water molecules. Okay, this is water. So we have, so water is going to be H2O. This because there's 2 hydrogens here and then 1 oxygen. And since there's 2 of these water molecules, that's why we put a coefficient of 2 here. Okay, and usually when we're like writing chemical equations, we will have to like write the states of everything. Okay, so you might be like not too confident in how to write down these chemical equations first, like as of yet, but that's why we're going to get into that more like coming up. So this is just a simple synthesis reaction, and we'll go into like we'll go more into depth of the different types of reactions later for this lesson. So in this figure above, all the reactants are on the left side of the arrow. So we have this arrow. This like represents so like on either side is going to be the reactants and the products. So to the left of it, of this arrow, we're going to have the reactants, and to the right, we're going to have the products. Okay. So we note that note that the number of individual reactant atoms is maintained in the products, okay, but are rearranged to a new form. So what this is trying to say is that we always, so in the reactants, we have 4 of these hydrogen atoms in the reactant side, and it stays the same in the product side. We have 4 of these hydrogens in the product side as well, okay, and it's same kind of thing happens with the oxygen atoms, okay, so we have 2 oxygen atoms as reactants and 2 of them as our products, okay. So that is that relates to this here. So since mass is conserved, the total number of each type of atom on the reactant side must be equal to the total number on the product side too. And this just relates to the law of conservation of mass that is stated in the syllabus top point. So if you ever like get a question on like why must the number of atoms be maintained in the product and reactants, like in an exam, you would relate it to the law of conservation of mass. And actually stating the law of conservation of mass will make your response a lot better, because actually in the syllabus, and it's like a subject-specific terminology kind of word or term. So that's the overview there. So we'll go like more into depth. So when writing chemical equations, it is important that to make it clear that we know what the reactants and the products are. So which chemicals are we like dealing with, and are they reactants or products? Okay, and we have to know the formula of them. So is it going to be like O2 or like maybe oxygen in a different type of form or a different number of oxygen atoms. Okay, so for example, we could like write table salt. Like if a question is talking about like table salt being just reacting with another type of compound, the correct formula is going to be NaCl. That's just like a simple example you might already know. Okay, so we also have to know the physical states. Okay, so this is usually at room temperature and pressure, so like usually around 25 degrees Celsius. So is it a solid, is it a liquid, or is it a gas, or is it dissolved in water? Is the certain substance dissolved in water? In that case, it will be aqueous. So it would be represented like this, AQ. Okay, so for the example of table salt, this would be solid. Okay, so solid, liquid, gas, or aqueous. That's what it's relating to when I say the physical states. Okay. So it is important that you remember to include whether an element is diatomic. Okay, so oxygen is a diatomic molecule, for example. Okay, in this example above, so we see that we don't just have a single oxygen atom like existing on its own; it's existing as a pair of oxygen atoms. That's just one molecule. Okay, it's gonna be O2. That's what we mean when we say diatomic. Okay, so diatomic molecules can easily be remembered through the mnemonic "Have no fear of ice cold beer." So you can like just forget about this O, this second O here, because we have like "Have no fear of ice cold beer." Okay, so that's like just one way to remember. Like I would remember that mnemonic because it will help you to remember a lot. So hydrogen is diatomic, nitrogen, fluorine, iodine, chlorine, and bromine. They're all examples of diatomic molecules. Okay. So when we have diatomic molecules, we have a subscript of 2 after the letter that represents that molecule or the term. Okay, so notice how we have 2's as subscript after every single element. That shows that it's a diatomic molecule. Okay, so we'll go into naming or like trying to determine the formulas of certain compounds and molecules now. So does anyone know what the formula for ammonium is? Like just guess it, or if you actually know what it is, you can just like put it in the chat. And if you don't know, that's okay, because you will learn this like in this module. Okay, so the formula for ammonium is NH4 plus. So ammonium, we call it a polyatomic ion. Okay, so this is what it's this is the formula for it. So it has a subscript of 4 because it's one nitrogen atom bonded to 4 hydrogen atoms, and it has a charge of +1. Okay, so this is ammonium, and I would recommend that you do remember like this specific formula for ammonium and some other polyatomic ions, which I'll get to later on. But ammonium is like one that you should try to remember because it does come up quite a bit. Okay, and it'll help you throughout like year 11 and 12. Does anyone know what the name of this one here is? OH minus. Any guesses? So OH minus is a hydroxide ion. Okay, so that's another polyatomic ion that you should try to remember. So it's just OH and it has a charge of -1. Okay, so like if you are dealing with like sodium hydroxide, for example, so NaOH, that's just Na with OH minus. Okay, so hydroxide is a very common polyatomic ion, so it's best that you do like remember the name and the formula for it. Okay, so then we have this this compound here. So we have SbBr3. Does anyone have any idea how we could name this? Any guesses? So this is so we can like just look at the formula for it. So we have Sb and then 3 Brs. Okay, so Sb, if we go to the periodic table and we look at the actual elements in the periodic table, Sb is antimony. Okay, so when you get your formula sheet in an exam, you can look at the periodic table and determine what their names are. So this is antimony. And then Br is bromine, if you look at the periodic table again, okay? So this exists as one antimony with 3 bromine molecules, okay? So how we write this, so we have to determine its name, we have to like just look at the number of the molecules. So we already know that we have 3 bromine atoms and 1 antimony one, okay? So looking at this, we can see that because we know that bromine has a charge of -1 because it's in the 7th group of the periodic table. We know that it's going to, so this molecule formed from this, so Sb, so antimony plus Br. So since Br has a charge of minus, and we don't know the charge of antimony, but we know that there's 3 bromine molecules, so we can put a coefficient here in front of the bromine, so it'll become Sb plus 3Br minus, okay? And this would mean that the charge of Sb, or antimony, is going to be 3 plus, okay? And the reason, so how I got that is because when we actually writing down the chemical formula for a certain compound, we take the charges and we like kind of cross them over. So we get SbBr3. If I just like write that down below, this minus will go like this, the 1 here. That's we can like write this as -1 here. This will go, the 1 will go here, and then the 3 goes down here. So that's how I determine that Sb has a charge of +3. That's just like one way you can think of it. But because I'm pretty sure Sb is a transition metal, so we don't like know, we can't just memorize like all of the different charges for the transition metals. That's just one example of how you can do it. Okay, so that's how we determine the charge of Sb. But to write down the name, does anyone know how we could write down the name for this? For antimony and 3 bromine atoms? So how we would do it is we would first write down the first the cation. So the cation here is going to be antimony, okay? And then for the bromine, there's 3 of them. So what we would write is tribromide. Okay, so we write tri because there's 3 of them. So that's the prefix for 3 of those atoms. It's tri. And then we write ide instead of ine because it's the anion in like an ionic compound. Okay, so that's the name for this molecule here, this compound here. And we can also rewrite this, okay? So we can rewrite this as antimony, and then instead of writing Tri, we can use Roman numerals. So inside brackets, inside some of the brackets, we can put in 3 I's, 3 capital I's, and that's the Roman numerals for it. And then bromide, okay? So those are like 2 of the ways you can write down the names for this compound here. Are there any questions so far? Okay, so moving on to this example. So we have xenon tetrafluoride, okay? So using like the same logic from this previous example, we can write down the name of the formula of the first ion, the cation. So that's going to be Xe from the periodic table. So if we find xenon, we'll know that the formula for it is Xe. And then we look at the second part of the name. So this tells us the anion. So the anion here is fluoride or fluorine, okay? And tetra, does anyone know how many atoms this is relating to? This prefix tells us. If tri is for 3, what would tetra be? You can like put it down in the chat if you'd like. 4, perfect, good job. So tetrafluoride, it's going to be 4 of them. So 4 fluorine molecules, okay? 4 fluorine atoms. So we can write it as F4, okay? We would write the 4 as a subscript, okay? So that's that example. And then we have carbonate. So this is another polyatomic ion. Does anyone like know off by heart what the chemical formula for carbonate is, or not yet? So so carbonate, the chemical formula for it is CO3 2-, okay? So the subscript of 3, and then a charge of 2 minus. So this is another example of a polyatomic ion that you'll come across like very frequently throughout year 11 and 12. So I recommend that you do memorize the formula for this one for carbonate, okay? So, the next example is this one. So we see that we have 3 copper atoms, and we have one of this whole PO4 in brackets, okay? Does anyone know what this in the brackets is called? What the name for that is? It's a polyatomic ion. But does anyone know the name of the polyatomic ion? So this polyatomic ion, its name is phosphate, okay? So this is phosphate. And this is copper, which you can just get from the periodic table. But hopefully you guys already know that this is copper. Okay, and we want to determine the name for it. So phosphate, the charge of phosphate is does anyone want to guess what the charge of phosphate might be? So the charge of phosphate is going to be 3 minus, okay? So if I just go here to the side. So we have PO4 3 minus. So this is just another example of a polyatomic ion where the charge you have to like memorize off by heart. Just like with carbonate and phosphate, you have to know this in this module. It's best to like know it off by heart. So if phosphate is 3 minus, then does anyone know what the charge of copper is? So copper is a transition metal. So some transition metals, they have a fixed charge, but other transition metals, their charges can like slightly vary, can vary in like different compounds and whatnot. So if we have 3 of these copper atoms and there's just one of these phosphates, and we know that the charge of phosphate is 3 minus, then that means that the charge of copper has to be 1 plus for it to become Cu3PO4. If we know that the charges like move to opposite sides when we do write down the compound. Okay, so that's how we get that. But moving back to the question, so if we're trying to find the name of this, it's the same kind of thing. So we have one of these polyatomic ions, right? One of the anions. So we just write it as copper phosphate. Okay, and you can write it as like copper phosphate, or you can use the Roman numerals like we did in the previous examples. So copper phosphate, or you can write copper 1. However, I would say that it's best to write down this second one, this second name, because copper, it does have varying charges, like I said. So copper can have like either a charge of like 1 plus or 2 plus. So I would say that writing down the Roman numeral is like the best way, just to ensure that you do get like full marks if you're ever asked in the exam. Okay, and then on to the last example. So it's the same kind of concept as the other one. So we have these prefixes of di and monoxide, and mono, sorry, in dibromine monoxide. So does anyone want to guess how many atoms would there be if we're talking about the prefix di? Just put it into the chat if you'd like. 2, perfect. So we have 2 bromine, and then what would mono be? How many atoms would that be? Perfect, it's 1. Okay, so we have 2 bromine atoms, and then we have 1 oxygen. So 2 Br and then 1 oxygen. So that just gives us the chemical formula of Br2 and then O. So those are just the examples that we have there. Does anyone have like any questions about any of them at all? Okay, so we'll just move on to some of like the key points we should know. So for transition metals, you need to specify their charges using Roman numerals. So for example, iron 3 chloride has the formula FeCl3. So whenever we have a transition metal like copper, So actually, in this example here, we wouldn't write just copper phosphate on its own. We would have to actually write the Roman numerals like here. So we have to specify that it's a charge of +1 by writing down just one I in these brackets, okay? Because otherwise the marker is going to be like, because you can just assume that copper could be 2+ unless you actually state that it's 1+. So that's why you have to actually state that so that the marker is like knows that you're not confused or lost or anything about it. Okay, so we have to specify the charges using Roman numerals. And also, it is important that at this stage you memorize the names and charges of the several polyatomic ions. Okay, so this includes nitrate, so that's NO3 minus, like here, and then also sulfate, SO4 2 minus, and I'll also write down some other polyatomic ions that you should know. So there's carbonate that we were looking at before. So carbonate is. Does anyone remember without like since you can't see it? Does anyone remember the formula for carbonate? You can just type into the chat. There's also ammonium, which we looked at. So carbonate is CO3 2 minus. So ammonium is NH4 plus. And then we also have phosphate, which we're looking at. And then another one that also comes up quite a lot is hydroxide. So these are like the most common ones, and it's important that you guys do remember this and memorize these off by heart because they come up quite a bit, not just in this module, but like throughout year 11 and especially in year 12. You're expected to like know this, like even in the HSC exam. They're not going to like give you the formulas for these polyatomic ions. You're expected to just like memorize it. So it's important that you do memorize it. So these are like the main ones that you should know. And then also another key point is that the states of different compounds depend on the strength of the intermolecular forces and covalent bonds. Okay, so when we're talking about states, we're just talking about like, is it liquid, gas, or is it like an aqueous, or is it solid? I think I missed. So did anyone want to guess like how the states would relate to the strength of the intermolecular forces? So like, why would the state depend on the strength of the intermolecular forces? You can just like type into the chat if you'd like. And does anyone know like are intermolecular forces between molecules or within molecules? You can just type that into the chat as well. So intermolecular forces, they're between molecules, okay? So if we have like water, the water example we were looking at before. So intermolecular forces are between different molecules, okay? So this would be like one of the intermolecular forces. This is a hydrogen bond in water, so the hydrogen is bonding to the oxygen atom in a different molecule, okay? So it's between molecules, it's not within. Like this wouldn't be an intermolecular force. This is the intermolecular force in this example, okay? So those are the intermolecular forces, and the states of different compounds, they rely on the intermolecular forces because the stronger the intermolecular forces, the more energy would be required to break apart those molecules. And so this would lead to like a higher boiling point and a higher melting point, okay? So that's like a point that you should remember. So stronger intermolecular forces means that we require needs more energy to break them apart. And this means that this can lead to like a higher melting point. and higher boiling point, okay? And this affects the states of the compound. Like, is it in a gas form? Like, if it has a higher melting point and a higher boiling point, then it would be in liquid and solid form. If it has a lower melting and boiling point, then it would be like at usually in gas form at room temperature. Sorry. Okay. So now we can move on to like writing balanced full formula equations. So there are different steps that we have to look at and have to follow when we're writing down these equations, okay? So the process for writing balanced chemical equations are as below. So we always begin with the unbalanced chemical equation, including correct formula and all states. Okay, so the first step we have to take is we have to write down the different chemicals and compounds that are involved, write down the formulas for them and their states, and it's like put them on either side of the arrow, depending on if it's a reactant and if it's a product. Remember, reactants are to the left of the arrows, and then products are to the right of the arrows. Okay, so the second step we will do after we write down those formulas and states is that we balance the elements that are only in compounds first. Okay, and the reason why we do this is that it will make it a lot easier, and you will understand why as we move onto some examples. But how I mentioned in the first step, how we have to include the states, this is really important because in an exam, if they ask you to actually balance an equation and you forget the states, then you might not get full marks for that question. So never forget your states. And there'll always be like a hint in the question as to what state, or you can just assume like with the knowledge, but there'll never be like a question where you can't answer it, or like you're unable to determine the state. Okay, so for step 2, this makes it easier if we balance the elements in the compounds first. And then afterwards, that's when we balance the elements by themselves, because this also makes it easier if we do it after. Okay, and then after that, we just check that the atoms and the charges are all balanced on both the products and the reactant side, because it has to be balanced. If we remember like the law of conservation of mass, okay? So look at the atoms, but also the charges. Do the charges add up? Okay. Are there any questions so far? Okay, we'll move on to an example now then. So we have this chemical equation that we have to balance, okay? So the first step we would do when trying to balance a chemical equation is that we would write the equation with the correct formula and the states, okay? This is like already been done in this example, but this is what we would do if we don't already know it. So we look at the compounds and we can see that it has the correct formulae and the states, okay? So this is iron oxide here, and it's in solid form. And this is iron, it's in solid form, and then we have oxygen gas. So all the states are there, so that's step 1 done. And then step 2, so since both oxygen and iron, they're by themselves, in the product side, we would balance the oxygen side, we would balance the oxygen first, since it exists as a diatomic molecule, but there are 3 present in the reactant side. Okay, and the reason why we do this, we don't have to do this, but it will make it a lot easier when you're trying to balance things out. It relates to like these steps, okay? So iron, when we balance that last, it just makes things easier because oxygen and iron oxide, they exist as like molecules that aren't just by themselves. So it's going to be a bit harder to balance. So that's why we do it first. Okay, so to balance the oxygen, we need to first consider the lowest common multiple between 3 and 2, because on the reaction side, there are 3 oxygen atoms, and there are 2 oxygen atoms on the product side. So we can already see that this is unbalanced, so we need to balance it, okay? So since there's 3 on the reactant side and there's 2 on the product side, we need to figure out the lowest common multiple between them, okay? And the lowest common multiple between 3 and 2 is going to be 6, right? So we need to determine a stoichiometric coefficient of 2 in front of iron oxide and a coefficient of 3 in front of this oxygen. Okay, and the reason is because to get 6, the lowest common multiple, we need to multiply 3 by 2, right? That's why we have this coefficient of 2 here. And then to get 6 from 2, we have to multiply by 3, right? That's why we have the coefficient of 3 in front of this oxygen gas here. Okay. Now we have to look at iron. So now we see that we have 4 atoms of iron on the reactant side. On the product side, we only have 1, so we have to do some balancing there. Okay, so to balance the iron, since there's 4 here and there's just 1 here, the product side would need a coefficient of 4. Okay, so that we can have 4 times 1 iron atoms on the product side, which is 4, which is equal to the number of iron atoms on the reactant side, which is 2 times 2, which is 4 as well. Okay, so now we can just double check everything to make sure that we haven't balanced incorrectly. So what I like to do is I just write down the different atoms. So for the reacting side, we have 2 times 2 ions, so that's 4 iron, right? And then we also have 3 oxygens. Oh no, we have 3 times 2 oxygens. So we have 6 oxygens on the reactant side, okay? And then now we just check the product side and see that they're equal, and then we'll be set, okay? So for the product side, we have 4 times 1 iron atoms. So we have 4 iron here. And then we have 3 times 2 oxygens. So we have 6, okay? So we can see that it's all balanced now. So this is the final equation. So it's going to be 2 Fe2O3, or 2 iron oxides, being converted into 4 iron and then 3 oxygen. Okay. So that's the final equation here. So we made sure that we have the correct formula. We made sure that we balance everything correctly and that there's an equal number of atoms of each of the atoms on the reactants and the product side. And we've included this correct states. So that's how we know we're done, okay? So a stoichiometric coefficient that I was talking about here, so 2, like 4 and the 3 here, they're the numbers that are written in front of the atoms or the ions and molecules, okay? And this helps us to balance the number of each element on both the reactant and product sides of the equation. So stoichiometry, it deals with the quantitative relationship between reactants and products in a chemical equation, like I was saying before, okay? So the stoichiometric ratio between iron and oxygen in this example is 4 to 3, okay? Because we have this coefficient of 4 here and this coefficient of 3 here, okay? So this means that for every 4 iron atoms that are formed in this specific equation, there are 3 atoms of oxygen gas that are formed, okay? So we actually use this stoichiometric ratio in when we're trying to calculate like quantities of a certain reactant or product form, like I was saying before. Okay, so for example, if we had 12 iron atoms, okay? If we had 12 iron atoms, how many oxygen atoms would there, oxygen molecules of O2 would there be, if anyone wants to guess? So if you have 12 iron, how many oxygen O2 molecules would there be? If we know that the ratio is 4 to 3. So what we can do is we can just write down this ratio underneath. So we have here, we're trying to find this oxygen, okay? So what we do is we divide this 12 by 4 and we multiply it by 3, okay? And this gives us 9. So there would be 9 of these O2 molecules, okay? And that is the same, so 12 to 9 is in the same ratio as 4 to 3, which is in this equation. So that's how we know if we produce 12 of these iron atoms, we would produce 9 of these O2 molecules, okay? Are there any questions about any of that at all? Okay, so we'll move on. So another way to keep track of the number of species present is by splitting the equation into respective reactants and products columns and comparing the numbers present. Okay, so we have the reactants here and the products here. Okay, so this is just another example, another chemical equation or reaction. So for example, if you have C3H8, we should not expect to like know the name of by heart yet. We'll like come across that in year 12. If that's reacting with oxygen, and it produces, like if there was an arrow here, it produces water and carbon dioxide. What we would do is we can write down like the number of each atom in the reactants and the product side, like how I was doing here, and it helps us a lot. So here we can just count how many of each atom is present. So here we're trying to calculate how many carbon atoms are present. So we can see that there's a subscript of 3 here, right? So there will be 3 carbons here, and then there's 8 hydrogens, and there's 2 oxygens, okay? So on the product side, we have initially we have 1 oxygen initially. For hydrogens, we have 2 initially, and then we have 3 oxygens here. Okay. And what we can do is we can multiply some of the compounds to make sure that there's an equal number of each atom on each side. Okay. So what we can do is we can multiply this oxygen by 4 and then add it to 2 plus 3, okay, to get 10 of these oxygen atoms. And then here we multiply this oxygen by 5 to get this coefficient of 5 here, okay? And so we're just trying to find like the lowest common multiple between this 2 and this 3 that we can use. Sorry, yeah, the 3 here. So we can get the equal number of oxygens on each side. Okay, are there any questions there? So we'll go through some more examples of balancing chemical equations to make sure it all makes sense. Okay, so for this example, we have to balance the equation where the reaction is a piece of zinc metal is placed in hydrochloric acid, and it produces aqueous zinc chloride and hydrogen gas. Okay, so in this example, we have a piece of zinc metal, okay? So we have to first identify the charge of zinc, okay? And zinc is, it has a charge of 2 plus. Okay, and I'll get to how you can also determine this if you don't like memorize off by heart, but what we know is that there is a piece of zinc metal, okay? So if it's a piece of zinc metal, it will just be existing on its own, so there won't be a charge, and it's just going to exist as a solid because it's a piece. So that's why it's Cn, and it's in a solid state, okay? And it's reacting with hydrochloric acid, and they give us the chemical like formula for hydrochloric acid there. And hydrochloric acid is an aqueous form. It's dissolved in water, okay? And then it produces, so that's why we have the arrow there. It produces aqueous zinc chloride here. So we know the state from the question. And it produces hydrogen gas as well. Okay, so how we can determine that here, that the charge of zinc is 2 plus, is that we know that chlorine has a charge of -1, okay? Okay, so chlorine has a charge of -1. So if this means if we have a subscript of 2 after this zinc here, then that means this 2 after the chlorine, it must be from a charge, it must be from the zinc having a charge of 2 plus, okay? So that's how we know that zinc has a charge of 2 plus, just from looking at the zinc chloride, okay? But I would say like try to memorize also the charges of different chemicals and compounds. Sorry, the charges of different transition metals, especially. Okay. So next, we're going to consider the atoms involved in in hydrochloric acid. Okay, and this is hydrogen and chlorine. Okay, so there are double the hydrogens and chlorines in the product side than the reactant side. Okay, so when we look at what we've written here, we can see that in the reactant side we have one hydrogen and one chlorine atom. Okay, but in the product side, we can see that there's a subscript of 2 here. So there's 2 chlorine atoms and there's 2 hydrogen atoms. So we can see already that it's unbalanced and that we need to balance it, okay? So this means that to balance it and to make sure we have 2 of these chlorine and hydrogen atoms on the reactant side, we need a stoichiometric coefficient of 2 in front of this hydrochloric acid in the reactant side, okay? So we just put a 2 there, for example, okay? Now to balance zinc. So we have both one zinc atom on this reactant side, and we have just one zinc atom on the product side as well. So since it's already balanced, we don't have to put any coefficients in front of these species, these chemical species, okay? So now we can just double check everything. So there's one zinc atom on both sides, there's 2 hydrogens here, and then there's 2 on the product side as well. And there's 2 of these chlorines on the reactant side and 2 on the product side, okay? So we can see that everything is balanced now. So we can just write down this final equation, which is just zinc reacting with 2 of the hydrochloric acid molecules, forming zinc chloride and hydrogen gas. Does that make sense so far? Are there any questions at all? You can just pop it into the chat if you like. Okay. So how I was saying that zinc, it has a charge of 2+. So some transition metals, they have varying charges. So if you remember from earlier how I was talking about copper can have the charge of 1+ or 2+. But with zinc, with other transition metals, their charges are fixed. So with zinc, it always has a charge of 2+. So you should just remember this for future, and in your module 2 exam, if you do have it in school, and even in year 12, it will help you memorize some of the charges of some of the transition metals. Okay, so this question was possible for us to do since we're able to recall that the charge of zinc was 2+. Okay, and it is important that you memorize the charges of such common transition metals. Okay, this includes aluminium, which always has a charge of 3+. Copper, it has that charge. It can be either 1+ or 2+. And then same for iron. It can have either a charge of 2+ or 3+, okay? And then I would also remember silver. Silver always has a charge of 1+, okay? And so when looking at copper and iron, how I was saying that it can have either a charge of 1+ or 2+ for copper or 2+ or 3+ for iron. It depends on the other element that it's reacting with in a compound with, okay? So you would always get a hint from the question whether it's going to be 1+ or 2+ or 2+ or 3+, okay? So are there any questions so far? Okay, so we'll move on to some examples now of actually balancing chemical equations. So the first question we receive is liquid heptane, and they give us the chemical formula for it. It's burning to form carbon dioxide and water, okay? So the first step I'm going to do is I'm just going to write down the reaction, what I do know from the question, okay? So we know that we do have C7, H16, that's liquid heptane, and it's burning to form carbon dioxide and water. But straight away, what I can notice is that there's oxygen atoms on the product side, but there's no oxygen atoms on the reactant side. And then I go back to the question, and it says that this liquid heptane is burning. Okay, when we're burning something, does anyone know what type of reaction what type of chemical reaction that would be, you can just type it into the chat if you like. So this chemical reaction, it's a type of combustion reaction, okay? When we're burning something in chemistry, the reaction is a combustion reaction, okay? And combustion reactions, they require oxygen gas, and that's why you see oxygen gas on this product side, okay? So we have oxygen gas reacting with liquid heptane. Okay, so now that we've got like the different different compounds and elements that we're reacting, all the reactants and the products, we can focus on the states of them. Okay, so with combustion reactions, the oxygen gas is always going to be in gas form. Okay, so you can write oxygen gas. We can write that state there, and then the question tells us that heptane is in liquid form. Okay, it says liquid heptane. So we can write this L here. That's how we indicate that something is in liquid form. And then it's burning to form carbon dioxide and water. So carbon dioxide, it's going to be in gas form, like how we usually encounter it. But for water, does anyone want to guess, would it be in liquid form or gas form if we're dealing with combustion, if we're burning? So water is going to be in a gas form. So even though we usually encounter water, yeah, perfect. So it's going to be in a gas form. So even though we usually encounter water as a liquid form, because we're burning liquid heptane in most combustion reactions, we're going to have water as a gas, and we can like sometimes see this as vapor or steam. So if you see like these, if you see these terms, it's usually relating to H2O in a gas form. Okay. So now that we've gotten all the reactants and the products and the states, we can now get to balancing this. Okay. So what I'm going to do is I'm going to write down each of the elements for the reactant sides and the product side. Okay. So I'm going to write oxygen, carbon, hydrogen on the reactant side, and then on the product side as well. Okay. So initially we start with 2 of these oxygen atoms, so there, and then we have 7 of these carbons, so that's going to be 7, and then we have 16 hydrogens. And then on the product side, we have 2 oxygens plus 1 here, so that's 3 oxygens. And then we have just 1 carbon here. And then we have 2 hydrogens. So we can see that there's a long way for us to go to actually balance this, okay? So the first step we can do is I'm going to start with water because I can see that there's like a very big difference between the numbers. So I'm going to start with the numbers of hydrogen, sorry. So we can see that there's 16 hydrogens on the reactant side and there's only 2 on the product side. So I would have to multiply the number of hydrogens on the product side by 8, right? So that I can get 16 because 2 times 8 equals to 16, okay? So I'm going to multiply this by 8. And how I'm going to do that is I'm going to put a coefficient of 8 in front of this water where there's only where it's the only place where hydrogen is present in the product side, okay? So I'm going to multiply by 8 by putting that coefficient there, okay? So now we have 16 hydrogens on the product side, okay? But now we have also changed the number of oxygen atoms, okay? So we can see that we have 8 of these oxygens here plus 2, okay? So we now have 10 oxygens, okay? And we can also see now that we've now there's a different number of oxygens on the product side and the reactant side, just like how it was before. But we'll deal with that after, because oxygen, we can see it's a diatomic molecule, and then it's going to be a lot easier for us to do it after we've balanced everything else first, because it's on its own on the reactant side, okay? So we'll deal with carbon, balancing carbon now. Okay, so we see that there's 7 on the reactant side, and there's only 1 on the product side. So we'd have to multiply the product side the number of carbons on the product side by 7 so that it balances out. And we can see that carbon is only present in this carbon dioxide on the product side. So we have to multiply this by 7, which means we have to put a coefficient of 7 here. Okay? And this changes the number of carbon and oxygen atoms on the product side. So we have to go back to this here and change it again. So we now have 7 carbons, and we have 7 times 2 oxygen. So that's going to be 14 plus 8. Okay, so that's going to give us 7 times 2 plus 8. That's going to give us 22 oxygen atoms on the product side. Okay, so we can see that now we have gotten to the stage where we've balanced hydrogen. We've got 16 on each side. We balance carbon. We've got 7 on each side, and we just have to balance oxygen. Okay, so does anyone want to guess how we would balance oxygen? What coefficient would I use and where would I put it? You can just put that into the chat. So I'm going, yeah, perfect. So I would have 11, right? And I'm gonna put that as the coefficient in front of this oxygen, of this O2 on the reactant side, okay? So the reason why we do that is because we see that there's 22 oxygens on the product side, but only 2 on the reactant side. So we have to see what can we multiply 2 by to give us 22. Okay, so you can also like look at it. If you can't like get that in your head, you can just do this. You can do 2x equals 22, and then you can divide both sides by 2 to give us 11. So that's the coefficient that we're going to use in front of this O2 on the reactant side, okay? So we can double check. So we have 11 times 2 oxygens on the reactant side, so there's 22 on the reactant side, and then 7 times 2 plus 8, that's also 22 on the product side. And then with carbon, there's 7 on the reactant side, and then 7 on the product side, and then hydrogen, it's 8 times 2 on the reactant of the product side, and there's also 16 on the reactant side. So everything's balanced, and we have our states for every single reactant and product. So now it's fully balanced, and we're done. Does anyone have any questions for that example? So usually we don't have to deal with coefficients that are this big. This is like one of maybe towards like a harder example that you might come across. But yeah, when you do write down like the number of atoms for each of the elements that are present on the reactants and the product side, and you do like this kind of thing, I think that it does help a lot. So that's just like one method you can do it, and that's what I find helps the most. So we'll move on to this example here, part B. Okay, so we have solid calcium carbonate reacting with sulfuric acid, producing solid calcium sulfate, water, and carbon dioxide gas. Okay, so calcium carbonate, does anyone know what the chemical formula for that would be? So calcium carbonate, we can just look at different cations and anions involved, okay? So we know that calcium, it has a charge of 2+ because it is in the second group of the periodic table, okay? So that's calcium 2+. And then carbonate, as I was saying before, it's best that you do memorize like these polyatomic ions. So carbonate is CO3 and has a charge of 2-. Okay, so that will just give us CaCO3 because these charges balance out, and we just get this. Okay, and the question tells us that it's going to be in solid form. Okay, and it's reacting with sulfuric acid. Okay, so sulfuric acid, it's going to be in aqueous form. Most of the acids that we come across, they're going to be in aqueous form. So they give us the chemical formula there. So that's going to be H2SO4. And to represent that as aqueous, we put AQ here. And then it produces, let me move this here. It produces, so this is where we draw the arrow because we're transitioning into the products now. It produces solid calcium sulfate, So calcium sulfate, again, calcium has a charge of 2+, and sulfate, if you remember from before, it's SO4 2-. So this is another polyatomic ion we should remember. So again, these charges will balance out. We'll just get CaSO4, and it says it's solid. Okay, so that's the state, and it's we're gonna also produce water, so H2O, and carbon dioxide gas. And water, so carbon dioxide is a gas, so like it says in the question. And water, it's going to be in liquid form because there's no like indication that it's going to be in gas form. It's not a combustion reaction, and it's not saying it's steam or vapor, so that's going to be in liquid form, unlike the previous example we encountered. Okay, so now we can just look at the different atoms and see if they're balanced. Okay, so we see that we're going to count calcium first. So calcium, there's 1 in the reaction side and there's 1 in the product side. Okay, so calcium so far is good. Now we can move on to another element. So we have carbon here. We see that there's only 1 carbon on the reactant side, and similarly, there's just 1 on the product side. Okay, so that's balanced. For the number of oxygens, we have 3 plus 4, so we have 7 on the reactant side, and on the product side, we have 4 plus 1 plus 2. That's also 7 oxygens. So that's balanced. Now let's look at hydrogen. So there's 2 here, and there's also 2 on this side. So that's balanced. And we've already looked at okay, then we have sulfur. So we have 1 sulfur here, and then 1 here. So that's balanced as well. And we've already counted oxygen. So it's already balanced. So we don't have to like do any coefficient. We don't have to put any coefficients or determine like the ratios. Okay, so it's all 1 to 1. So that's the finished chemical equation, and it's already balanced. Does it make sense? Are there any questions for that one? Okay. Now we have this example. So we have solid magnesium oxide forming when magnesium metal reacts with oxygen. Okay, so with this question, even though it has magnesium oxide being stated first in the question, that doesn't necessarily mean it's a reactant. Okay, so when we look like after magnesium oxide, it says it forms when. Okay, so that this indicates that magnesium oxide is not a reactant, but it's a product. Okay, and it's forming when magnesium metal reacts with oxygen. So these are 2 indicators: the forms when and that reacts with. These are 2 indicators that suggest that magnesium oxide is a product and not a reactant. Okay, so let's look at the reactants. We have magnesium metal. Okay, and when we have something existing as a metal, it's going to be stable. So it's not going to have a charge. So it's just going to be Mg, and it's going to be solid in solid form because it's a magnesium metal, and it's reacting with oxygen. Okay, so it's going to be reacting with O2 gas, and it forms magnesium oxide. Okay, and does anyone know the chemical formula for magnesium oxide? Just type it into the chat. Yeah, perfect. It's MgO. And if you don't know this like off by heart, how you could determine it is you can just write down Mg, which has a charge of 2+, because it is in the second group of the periodic table. So Mg is 2+, and then oxygen has a charge of 2-. Okay, so their charges, they balance out and they cancel out, and we just get MgO. So that's the chemical formula for magnesium oxide. And then that's in solid form because the question says it's in solid form. Okay, so that's the state. We've got all the states down so far. Now let's look at how we can balance this. Okay, so immediately I can tell that there's 2 oxygens on the reactant side, but only 1 on the product side. So this means we have to balance. Okay, so I'm gonna write down the number of atoms for each element for the reactant side and the product side. It's gonna be magnesium and oxygen here, and it's forming magnesium oxide. So I can count the number of magnesiums. So on the reactant side, there's 1. On the product side, there's also 1. But for oxygen, there's 2 on the reactant side, but only 1 on the product side. So this means I would have to multiply this magnesium oxide by 2. So I can get 2 oxygen atoms. And so this would give me, this will multiply both magnesium and oxygen by 2. So I get 2 magnesiums and 2 oxygens. And now I can see that magnesium, that even though oxygen is balanced, we can see that magnesium now is unbalanced. We have to balance magnesium now. Okay, so we can see that there's 2 on the product side, but only 1 on the reactant side. So can anyone tell me what would the coefficient be in front of this magnesium here? So that it balances out. 2, perfect. Okay, so I'd have to multiply this magnesium by 2. So this would give me a coefficient of 2 in front of this magnesium. Okay, we can just double check. There's 2 magnesiums here, there's 2 here, and there's 2 oxygens here, and there's 2 oxygens on the product side as well. Okay, so that's the balanced chemical equation for this reaction. Are there any questions so far? Okay, so we'll move on to the second major part of the syllabus 12 point we'll be focusing on. So this is the common chemical reactions, okay? So the syllabus tells us that we have to conduct investigations to predict and identify the products of a range of reactions, okay? Okay, so this includes synthesis, decomposition, combustion, precipitation, acid-base reactions, and acid-carbonate reactions, okay? So since the syllabus dot point, it states all of these reactions, that means you have to know all of them, okay? You have to know each of them, and specifically you have to know like what type of reactants would be involved and what are the products that are commonly produced in these reactions, okay? So in class, you might do experiments on each of these reactions, okay? So that's why it says conduct investigation. So it's actually a practical experiment that you will probably do in class, okay? So let's start with our synthesis and our decomposition reactions, okay? So in a synthesis reaction, we have more complex substances being produced from simpler ones, okay? So you can like tell from the name, we're synthesizing something. So we get like less complex, like simpler reactions forming and synthesizing a more complex substance or compound. So this is like just a general equation. So we usually have more reactants, usually, and they're forming less products usually in synthesis reactions, okay? So this is just one of the examples. So we have hydrogen gas reacting with oxygen gas, and this is forming water vapor, okay? So this is just steam that's being produced because it's in a gas form. So even though it's water, it's in a gas form, so we can call it steam or vapor, okay? Or water vapor, okay? So the formation of steam hints to us that water has been formed but in a gas form, okay? So we know that hydrogen and oxygen are diatomic molecules. If you remember, we have H2, so have no Phe, I square B, so N2 and this Br2, and pretty sure this is Cl2. We go back. So yeah, so we have this mnemonic, have no fear, bicycle B. So hydrogen, nitrogen, fluorine, iodine, chlorine, and bromine. These are all of our diatomic molecules. So we know that hydrogen and oxygen. Yeah, oxygen is also. I missed oxygen. Yeah. So oxygen is also a diatomic molecule. Okay. So as a result, we needed to balance the equation using stoichiometric coefficients for hydrogen to obey the law of conservation of mass. Because the number of atoms in the reactants must equal the number of atoms in the product side, okay? And that's exactly why we balance our chemical equations, because of this law of conservation of mass. So that's like the most important part. Okay, so the second type of reaction is a decomposition reaction. Okay, so like you can look at it as like the opposite of a synthesis reaction. So we're decomposing something, we're breaking it down. So more complex substances are broken down into simpler ones. Okay, so it is the reverse of synthesis. So we have a more complex substance and it's broken down into more simple substances. Okay, this is just the general equation. So that's decomposition. Are there any questions so far? Okay, so in this example, we have to write the balance equation for the electrolysis of water. So this is the balance equation here. And electrolysis, it's just referring to the splitting of water into hydrogen and oxygen. When we're talking about water electrolysis, so it's just splitting. I write that needle. And oxygen. So in this case, the decomposition reaction is the exact reverse of the synthesis reaction that we were looking at here. Okay, so there's a coefficient of 2 in front of the hydrogen and a coefficient of 2 in front of this water that we can see here. So that's what it's trying to say when we that's what we mean when we say that synthesis reaction is like the reverse of a decomposition and vice versa. Okay. So the decomposition of water can be done through the process of electrolysis, as I was mentioning here. Okay. So that's decomposition and synthesis done. We'll move on to precipitation now. Okay. So as you should already know, a solution is a homogeneous mixture of a solute and a solvent. Okay. So usually, like we have the solute is the thing that's dissolved in the solvent. Okay. So if we're talking about like the solute, for example, if it's sodium chloride, if we're talking about table salt, it could be dissolved in water, for example. Okay. So if we have solid sodium chloride reacting with water, it would form a solution of aqueous sodium chloride solution. Okay. So the this state here would actually change to aqueous. That's for a solution. Okay, so that's what it's saying here. So the state in which a solution where water is the solvent is referred to as aqueous. Okay, so this is a very important point. So it is denoted by the subscript AQ in a chemical reaction. This is the state that it's in. It's not solid, it's not liquid, it's aqueous, which is separate. Okay, so when two aqueous solutions mix, sometimes a solid is deposited at the bottom of the reaction mixture after it settles, or the mixture becomes cloudy. Okay, so this process is called precipitation. This is the whole reaction. And the deposit is referred to as the precipitate. Okay, so it's just like a solid substance that is produced when we mix two aqueous solutions. Now, this doesn't always happen in every single this doesn't happen every single time we mix aqueous solutions. It just depends on the solubility of the compounds that are produced. Okay, so in a precipitation reaction, there is a swap of the ions in the ionic compounds, thus also being called double displacement reactions. So if you ever forget like what's happening in a precipitation reaction, or you don't know what exactly is going to be formed in the products, you can look at the reactants and you can remember the term double displacement reactions. So double displacement reactions is just another way of saying precipitation. So one way you can look at it is we have sodium and hydroxide ions, so sodium hydroxide and calcium bromide as a reactants. So since it's a precipitation reaction and it's a double displacement reaction, what will happen is that this cation in this compound will react with the anion of the other reactant, and they will form sodium bromide. And then similarly, the cation of the other substance will react with the anion of the other compound, forming calcium hydroxide. That's what it means by double displacement reaction, okay? So all precipitation reactions are double displacement. So the cations and the anions of the reactants, they swap around, okay? And that's just what this color kind of table is trying to indicate. So sodium and bromine, they react to form sodium bromide, and then calcium and hydroxide, they react to form calcium hydroxide here, okay? So we can see here that it's actually unbalanced. We can see hydroxides unbalanced. So to balance this equation, we can put a coefficient of 2 in front of the sodium bromide and this coefficient of 2 in front of this sodium hydroxide, which if you just perform the steps from before, you can reach this balanced chemical equation, okay? So one thing to note is that the precipitate, it's less soluble. It's like an insoluble substance that is formed, okay? So if we form the products and they're soluble, meaning they can be dissolved in that solvent, then no precipitate will form. But if we form products where one of them is insoluble, that's when a precipitate is formed. The insoluble compound becomes a precipitate. Okay, so that's what it's trying to say here. So precipitates are always less soluble than the original solution that they came from, and they're always in solid form, okay? So as we can see in this reaction, this precipitate is going to be calcium hydroxide because it has this solid form that's produced from the mixing of two aqueous solutions. So the precipitate formed in the above reaction, as it's saying here, is calcium hydroxide, and it's observed as a white solid suspended in the solution. Okay, so by the time you reach your HSC exams, like any 12, you would know like the different types of like the different colors that a precipitate will form depending on its chemical formula. So like you usually come across like white precipitates, brown precipitates. If you have copper, you usually come across blue precipitates. So there's different colors representing like whatever precipitate it is. And you also like know some solubility rules. So we'll get to that now soon. So this is what happens when we mix sodium hydroxide and calcium bromide. So we can see if we do it in a test tube, we'll see that this white solid is being formed, okay? It's the precipitate. Okay, so as I was saying, so you can predict whether precipitate will form or not using the solubility rules. And these will be learned in more detail later in the chemistry course, okay? So most likely, like you won't be expected to know what in too much depth just yet, unless your teacher asks you to. But yeah, you'll come across some solubility rules, and there's a lot of acronyms and mnemonics that you'll come across. Like for example, NAGSAG, Castro Bear. But you don't have to like know these now. These are just like some of the examples that you'll come across later in PMS. And they just tell you like which chemicals are going to be soluble and which are going to be insoluble, okay? So you don't have to like memorize that too much now. Okay, so now we'll just go into balancing some equations. Are there any questions so far? Okay, so we have to write the balance equation for the following. So for part A, we're given that blue copper sulfate solution, it reacts with potassium carbonate to produce a blue precipitate, okay? So we'll write down what we're already given in the question. So we have copper sulfate solution, okay? And it tells us what would be the charge of copper in this case. Remember how I was saying copper can have a charge of 1 plus or 2 plus? In this example, what would be the charge of copper? So remember how I was talking about these Roman numerals? So copper will have a charge of 2 plus because of this Roman numeral 2 here. Okay, so it would be copper 2 plus reacting with sulfate. Remember how I was saying sulfate is SO4 2 minus? So this will give us copper sulfate as one of the reactants, okay? And it's reacting with potassium carbonate, okay? So potassium it's in the first group of the periodic table, so it's going to be +1, and carbonate is going to be CO3 2-. So this would give us K2CO3. And this is because this charge of 2- is going to transfer, and we're going to need two potassiums to balance it out and give us a neutral charge. That's why we have two of these potassium atoms in potassium carbonate. Okay, so it's going to react with potassium carbonate, and they're just going to be it doesn't say any of them are solid, so they're both in aqueous solution, and it's going to produce a blue precipitate. Okay, so it doesn't tell us what type of products is present. Okay, but what I was saying before is that precipitation reactions are actually double displacement reactions. Okay, so if you remember, so if you can tell that this is a precipitation reaction because we're dealing with a precipitate, so it's producing a blue precipitate. So that's how we know that this is a double displacement reaction. Okay, so does anyone want to guess what are the products that are going to be formed? And like, you don't have to tell me the states. Just what would be the products that would be formed from this precipitation reaction? You can just type into the chat if you like. Okay, so the products are going to be the cation of one substance reacting with the anion of the other substance. Okay, so it's going to be copper 2+ reacting with carbonate, so the charges will balance out, so we just get CuCO3, that's copper carbonate, and it's going to also produce potassium sulfate, and this is going to be K2SO4 because sulfate has a charge of 2- and potassium only has a charge of 1+. Okay, so K2SO4, potassium sulfate. Okay, so those are the products that are going to be formed. Remember how I was saying this is a double displacement reaction? That's how I got these products. Okay, if you have any questions, just let me know. But those are the products that are going to be formed. Now we're not done yet because we haven't included the states for each of the products and reactants. Okay, so it does tell us that the precipitate is blue. Now, does anyone want to guess if a precipitate is blue, which element would be present? If you guys know from earlier examples, or if you were paying attention earlier, what I was saying with the precipitate colors. So usually when we have a blue precipitate, it's going to involve the cation of copper. Okay, so copper precipitates are usually blue in color. So the fact that the question tells us that the precipitate is blue indicates that it's going to be copper carbonate that's going to be precipitating. Okay, so even without knowing the solubility rules, you can still determine what's going to be precipitating. Okay, so if copper carbonate is precipitating, then potassium sulfate must be the aqueous solution that is also being produced. Okay, and we can look copper, there's just one on each side. There's one sulfate polyatomic ion, there's two potassiums, and there's one carbonate. So this is fully balanced. Okay, so that's how I got this equation. Okay, does anyone have any questions so far? Okay, so we can move on to the next example. So we have iron chloride solution reacting with lithium phosphate, solution to produce iron 2 phosphate as a precipitate. Okay, so we have iron 2 chloride. So this is going to be Fe2+. We know that chlorine has a charge of 1- because in the 7th group. Okay, and then because it has a Roman numeral of 2, we know that in this case iron has a charge of 2+. So that's going to give us FeCl2. It's a solution, so it's going to be aqueous, and it's reacting with lithium phosphate solution. Okay, we know that lithium is in the first group of the periodic table. Okay, if you look at the formula sheet, so that's going to have a charge of +1, right? And then phosphate, we should remember the charges and the formulas for the polyatomic ions, like these examples. So it's going to be charge of 3 minus. So it's going to be 3 Li, so 3 lithium, so Li3, and then PO4. Okay, and it's going to produce iron phosphate as a precipitate. Okay, so it tells us what's precipitating. So Fe2. So we have Fe2 plus reacting with PO4 3 minus. So this charge of 3 is going to mean we have 3 of these Fe, of these iron atoms being produced. And then this charge of 2 plus, we're going to have 2 of these phosphate polyatomic ions. Okay, so how we write that is we would put the phosphate in brackets, and then outside of these brackets, we put the subscript of 2. That's how we indicate that there's 2 of these phosphate polyatomic ions. Okay, so we have one of the products. And remember how I was saying the double displacement thing? So we have iron phosphate being produced, but we also have lithium chloride being produced, okay? And the lithium and chlorine, they both have a charge of 1, so it just balances to form lithium chloride, LiCl. Okay, and it told us that iron phosphate is a precipitate, so that's going to be solid form, okay? And then the lithium chloride is going to be aqueous, since the iron phosphate is solid, okay? And the lithium phosphate is going to be aqueous as well, because these two solutions are reacting. Okay, and we can see that this specific reaction is unbalanced, okay? This equation is unbalanced. We have to balance it because we can see there's already like 3 iron on the product side, and there's only 1 of those iron atoms present on the reactant side. So what we can do is we can, again, write down the number of each atom on each side of the reaction. So iron, chlorine, lithium, and then I'm going to do phosphorus and oxygen separately. So same for the reactant, the product side, sorry. Okay, so for iron, we see that we have 1 here and then 3 here. Chlorine, we have 2, and then 1. Lithium, 3, and 1. Phosphate, just 1, and then 2 here, and then 4 on the reactant side, and then 4 times 2 here. That's 8. Okay, so what we can do first is we can we see that there's 3 iron atoms on the product side, but only 1 on the reactant side. So we have to put a coefficient of 3 in front of iron chloride to make sure we have 3 of these iron atoms, so that iron is balanced on each side. But this also changes the number of chlorine atoms, okay? So now there's going to be 3 times 2 chlorine atoms. That gives us 6 chlorine atoms, okay? Now this messes up the balancing of the chlorine atoms because on the product side we only have 1, so we have to multiply lithium chloride by 6 as well, right? We have to have a coefficient of 6 as well here. Okay. So now we can look at lithium. Lithium here is there's 3 of them here, and now there's 6 here. So we have to multiply this by 6. 6. So how can we balance the lithiums? What coefficient would I need to put, and where would I put it? Does anyone want to guess in the chat? So we would get a coefficient of 2 in front of this lithium phosphate on the reactant side. Okay? So that because 2 times 3 is going to give us 6 so that we can balance the lithium. Okay? So we multiply this lithium by 2, gives us 6, and it also changes the number of phosphorus and oxygen atoms. So we can calculate that. So 2 times 1 phosphate is going to give us 2, and then 2 times 4 oxygens. That's going to give us 8. So now let's look at everything. We have 3 iron atoms on each side, 6 chlorine, 6 lithium, 2 phosphorus, and 8 oxygen. So that is the balanced chemical equation for this reaction. Are there any questions so far on like anything I've done leading up to this? Okay, so we can move on to the second type of reaction. So we have combustion reactions, okay? Not the second type, like a different type, sorry. So combustion reactions is the reaction of a substance with oxygen gas, if you remember from earlier, okay? We're reacting something with oxygen gas. And burning is a type of combustion, and combustion reactions are subsequently used for heat production, okay? They're exothermic usually. So in some cases, let's write that here. Exothermic. So in some cases, they can act as very bright sources of light. So in class, if you do like the burning of magnesium as a combustion reaction example, you'll see like you hear your teachers like tell you do not look at the light because it produces a very bright light when you burn magnesium. That was the example we were looking at before with the burning of magnesium producing magnesium oxide. So you'll see like, a very bright light and it's so bright that can least like temporary blindness, I think. So do not look at the light. But different conditions will produce different products, okay? So for example, the yellow safety flame that we can see here of a Bunsen burner indicates incomplete combustion and thus does not produce as much heat. So we have incomplete combustion and it doesn't produce as much heat, okay? And it also produces carbon soot alongside carbon monoxide and water. Sometimes you'll only come across like it producing carbon soot or just carbon monoxide. However, when we have the blue heating flame, so that we can see here, this indicates an abundance of oxygen and thus complete combustion, producing carbon dioxide and water. So this is important. So when we have enough oxygen, when oxygen is not a limiting reagent, then this allows for complete combustion, okay? And complete combustion always produces these products, carbon dioxide and water. And you actually have to memorize these products, okay? So carbon dioxide and water is the products for complete combustion, and carbon soot or carbon monoxide and water are the products for incomplete combustion when there's not enough oxygen. And that also doesn't produce as much heat. So these are the Bunsen burner flame colors. Okay, so for this example, we have incomplete combustion and complete combustion of this gas, methane, okay? So we can see that the coefficients are different. Okay, so we see like 2 methane gases for incomplete combustion and just 1 for complete. So that's what happens when we don't have like enough oxygen. Even though there's like even though there's a coefficient of 3 here, it's not producing like as much heat or like the same product. So it's a bit different. That's why it still means that there's not enough oxygen in the incomplete combustion. Okay, so note that the water formed is in gas state. Okay, so it will be a water vapor. Okay, so that's what I was talking about before. So water, if it's in a gas state, it's gonna be like represented by water vapor or steam. So this is because combustion reactions involve very high temperatures. So incomplete combustion equations don't necessarily have to form both carbon soot and carbon monoxide, as I was saying before. So it is acceptable to only include one of these in your equation for simplicity, as having both in your equation can make it very difficult to balance the equation. So the above example assumes only carbon monoxide is formed. Okay, are there any questions so far? Okay, so we'll move on to the, a different type of chemical reactions that you do have to know for this module. So we have acid metal and acid carbonate reactions. Okay, so acids are chemicals that contain hydrogen. They commonly contain hydrogen. Not all acids will involve hydrogen, but usually for module 2, you will just come across acids that do contain hydrogen. Okay, and so like we can think of some common examples like HCl, which is hydrochloric acid, or H2SO4, as we were looking at before, which is sulfuric acid. But yeah, you can see that there's usually hydrogen in these acids, and this allows them to have many chemical reactions with the surrounding matter in the environment, so they become reactive. So in acid and metal reactions, acids react with active metals to produce an aqueous salt and hydrogen gas. So this is you should remember these products involved. So when we react acid plus metal, we get a salt, that's in aqueous form, plus hydrogen gas. So you should remember this like general equation for acid metal reactions. Okay, and this hydrogen gas, it can be seen as this bubbling here. When you do it in like a test tube. Okay, so hydrogen gas, it can be tested for using the pop test. Okay, so hydrogen is a flammable gas and it burns quickly when exposed to oxygen. So lighting a match in a test tube filled with hydrogen gas will create a pop and cause the match to go out. Okay, so when you do perform these reactions in class and you do the acid metal reaction and you put, like for example, a strip of magnesium into some hydrochloric acid, for example, you can like observe the metal, it will produce bubbles, okay? And you can prove that this is an acid metal reaction by lighting the match above the opening of a test tube. Okay, so this is just the match. And what will happen is this will, if there is hydrogen gas being produced, it will produce a very loud pop sound. Okay, so it's a very distinct sound. Like you will definitely notice it's unique to like other sounds. It's pop sound, and it causes a match to go from like on fire to just it goes out. Okay, that's like one of the tests for the acid metal reactions, and we have a test for the acid carbonate reactions as well, which we'll go into later. Okay, so for this example, we have to write the balance equation for the reaction between zinc and hydrobromic acid. Okay, so we have zinc metal is reacting with this acid, hydrobromic acid, and it's going to form this aqueous salt and hydrogen gas. Okay, just like how we're looking at this this general equation for acid metal reactions. Okay, so the metal reacting with an acid, forming the aqueous salt and hydrogen gas. Okay, so a term you'll come across commonly in module 2 is effervescence, usually like with acid metal reactions. So it is the state of giving off bubbles. Okay, so as the reaction between acids and metal carbonates or metals or carbonates will be effervescent. So greater effervescence is associated with greater reactivity of metals. Okay, so the more reactive a metal is, the more bubbles will be produced. Okay, so and that's like the more effervescence that you will see. So if you're like asked in an exam, like what are the signs that an acid metal or an acid carbonate reaction occurred, you could state like effervescence or the presence of bubbles, and that indicates that a chemical reaction actually occurred. And you can prove this by using a pop test or a light and water test, as we'll see with acid carbonate reactions. Okay, so that if you ever are asked that in an exam, that's some of the things you could write down. Okay, so metal reactivity can be generalized using trends in a periodic table. So like I'm just gonna draw like, if you look at the periodic table, how it actually is, it looks something like this. I don't actually have it on me. So metal reactivity, it decreases from left to right. Okay, so left to right, it decreases. And it increases from top to bottom. So this is some of the trends that you should know. This will help you, like you might get asked this in an exam, so you should know that metal reactivity, it decreases from left to right and it increases from top to bottom. And like one way you can memorize this is, I think like somewhere down here is the element francium, which is like somewhere in this bottom left corner, okay? And so that's how you know, since it's like towards the bottom and it's towards the left, that's how you can like remember that the trends of the metal reactivity. Okay, so remember that the more reactive metal is, the more bubbles that it will produce. So the more effervescence you will observe. Okay, so the next reaction is acid carbonate reactions. Okay, so they react to form a salt, carbon dioxide gas, and water. Okay, So we have an acid plus carbonate. So it's going to be like, in this example, sodium carbonate. It's reacting to form a salt. This is the salt here. Plus carbon dioxide gas plus water. And it will be like, this water will be in liquid phase. Okay? So that's the general equation that you'll come across with acid-carbonate reactions. Okay, so the test for this reaction is through funneling the carbon dioxide gas into lime water to observe the solution becoming cloudy. And this result is due to the formation of the precipitate calcium hydroxide. So if you remember previously how I was mentioning the POP test for acid metal reactions, the test to prove an acid carbonate reaction is the lime water test. So this is what is referring to. So it's the lime water test. So lime water is just this solution that's usually colorless, okay? And when we funnel the gas that forms in this acid carbonate reaction into a solution of lime water, the lime water would turn from colorless to like almost like a milky white kind of like cloudy solution, okay? And that's how we prove because it turns from colorless to cloudy because of the presence of carbon dioxide. And since carbon dioxide is like a distinct product of acid carbonate reactions, this is another way we can prove that an acid and carbonate reaction actually occurred. Okay, so that's the lime water test. You should remember this. So in this example, we have to write the balance equation for the reaction between sodium carbonate and hydrochloric acid. Okay, so we already know that for acid carbonate reactions, they produce a salt. This is here, a carbon dioxide gas, and water as a liquid form. Okay, and we can just balance it using the skills that we learned earlier today. Okay, so acid carbonate reactions are also a special type of neutralization reaction, which we're going to go through here. Okay, so the reaction between an acid and a base is called neutralization. So when an acid reacts with a base, and it results in the formation of water from a hydrogen ion and hydroxide ion. So usually the hydrogen ion comes from the acid and the hydroxide ion comes from the base. And this forms water as a product, okay? This is for neutralization reactions. And so neutralization reactions, they form an aqueous salt, water, and heat. So since it produces heat, usually in neutralization reactions, they're exothermic, okay? Okay, so this is from the acid, the hydrogen ion, and this is from the base. Are there any questions so far? Okay, so we'll go through this example. So we have to write balanced chemical equations for the following. So for part A, it says pellets of sodium hydroxide base react with an acid to form potassium sulfate and water. And I'll just fix this here. This is potassium, it's supposed to be potassium hydroxide. Just a little typo. So pellets of potassium hydroxide react with a certain acid to form potassium sulfate and water. Okay, so what we can do is we don't actually know the presence, we don't actually know what type of acid is reacting, okay? So we have to determine this on our own, okay? So what we can do is we can write down the base, potassium hydroxide. So that's going to be KOH because potassium has a charge of 1 plus, hydroxide has a charge of 1 minus, and it's going to be solid form. And the reason why it's solid form is because it says it's existing as pellets, okay? So it's reacting with an acid to form potassium sulfate, which is going to be K2SO4. And this is going to be in aqueous form because it's, the salt is in aqueous form in neutralization reactions, and it will produce water. So that's going to be H2O. And it's also going to produce heat because it's exothermic, okay? So we can see here that to determine the acid, we can see that the salt that's produced is potassium sulfate. And so this sulfate has to have come from the acid sulfuric acid or this sulfate, okay? So that's how we can determine the acid that's reacting with the potassium hydroxide. Okay, and so that would be in aqueous form. Now to balance it, we can see that there's going to be there's 2 potassiums on the product side, but only 1 on the reactant side. So we have to multiply this potassium hydroxide by 2. Now we can also see that the number of hydrogens is 2 on the product side, and then it's going to be it's 2 here on the product side, but then on the reactant side, it's 2 plus 2, it's 4. So this is unbalanced. So we have to balance it. And what we can do is we can multiply this water by 2 so that we can get 4 hydrogens on the product side and then 4 on the reactant side. So that's balanced. So now this equation is fully balanced. So there's 2 potassiums on each side, 4 hydrogens, 4 plus 2 oxygens, so that's 6. And then hydrogens, there is 2 plus 2, there's 4, yeah. Okay, so that's completely balanced. Okay, so does that make sense how I balance that? Are there any questions, sir? Okay, so I'll skip this example and we'll move on to the mole because we're just running out of time. So for the mole concept, so we'll go through the syllabus dot point. So we have to explore the concept of the mole and relate this to Avogadro's constant to describe, calculate, and manipulate masses, chemical amounts, and numbers of particles in moles of elements and compounds. So one formula that you'll come across a lot is this one. So the number of moles is equal to the mass in grams here over or divided by the molar mass in grams per mole. And this molar mass, you can usually find it on the periodic table, or you can calculate it using the periodic table, okay? So we are used to generalizing large quantities under terms like dozens, centuries, millennia, and etc. Okay, so in chemistry, we are dealing with huge amounts of molecules, and thus we've come to the term mole, and this has been used to represent a specific quantity of any substance. Okay, so this concept is very important for chemical calculations, and in chemistry, a mole is defined to contain 6.022 by 10 to the 23 of some form of matter. So this this quantity can be associated with an atom, ions, or any particles. And this specific number is Avogadro's number. So this 6.022 by 10 to the 23 is Avogadro's number. And this is 1 mole of a substance. Okay? I would recommend that you do memorize this specific number, but if you don't, it's actually on the first page of the formula sheet, 6.022 by 10 to the 23 moles. Okay? So there's a YouTube video that you can watch in your own time. It's just a TED video on moles. So we'll go over the Avogadro's number. So Avogadro's number, 6.022 by 10 to the 23, is really important as it allows us to convert between moles and a quantity of matter using this equation, okay? So this is like the number of moles is equal to the number of particles over Avogadro's number, which is 6.022 by 10 to the 23, okay? So to convert from particles to moles, we can divide by Avogadro's number, and to convert from moles to particles, we multiply by Avogadro's number, okay? Using this equation, and that's how you can determine that. Okay, so for this example, we asked how many moles are there in 1.626 by 10 to the 23 molecules of sodium hydroxide. Okay, so using this equation here, the number of moles that we're trying to find, that is equal to the number of particles, which is 1.626 by 10 to the 23 molecules of sodium hydroxide, divided by Avogadro's number, which is 6.022 by 10 to the 23. And when we calculate that, we get 0.27 moles. Okay, I don't think it's exactly 0.27, but we do round it to those 2 significant figures. It might be 0.27, but yeah. So it is important that you memorize Avogadro's number as it will be used, as it will be involved in many calculations in chemistry, okay? So you can memorize it. It's going to help you a lot. It's going to be a lot quicker if you memorize it compared to if you just look at it and like constantly look back to the formula sheet, but it is on the formula sheet in case you do forget it. Okay, so the mole is also related to the concept of relative atomic mass, as 1 mole of any substance is its relative atomic mass in grams. Okay, so this can be sourced from the periodic table. Okay, the periodic table, it gives you the molar mass in grams per mole. So if you look at the periodic table, if you have it with you, for example, if you look at carbon, so carbon's at the top of the fourth group, I think, and we can see 12.01. So the number below the chemical formula is the molar mass. So in carbon, that's 12.01. If you look at the periodic table that you're given on the formula sheet, that's the molar mass there. It's below the formula, the name or the chemical formula of that element. Okay, so that's on the periodic table. It's given to you. So we're going to do some questions. So this question asks us, what is the mass of 1 mole of fluoride atoms? Now this question is relating the number of moles to the mass. So we don't actually use this because this formula here, because this one doesn't relate to mass, but rather we relate it to this formula that's in a syllabus. So that formula is number of moles is equal to the mass over the molar mass. Okay, so so we're trying to find the mass. So what we can do is we can multiply the molar mass by the number of moles to find the mass. So the mass will become the number of moles times the molar mass. Okay, so the mass is in grams, and it's equal to the number of moles, which is 1 in this case, times the molar mass of fluoride atoms. So the molar mass of fluorine, if we go to the periodic table, look at fluorine, we have 19.00. Let me know if you have any difficulty trying to find the molar mass. So it's under F on the periodic table. That's 19.00. So the mass is going to be, the mass is going to be 19 grams. Okay. So that's the mass of that's involved in 1 mole of fluoride atoms. Okay. In this next example, we're asked what would be the mass of 3.011 by 10 to the 23 helium atoms. So the same concept that we do here. So we can do the mass is equal to the number of moles times the molar mass. Okay. So the mass is going to be the number of moles, and this time the number of moles. Oh, actually, it's not going to be the same equation. Okay. So it's going to be the number of moles. Sorry, we would do this, yeah. So we would have to find we would use this formula, so mass equals the number of moles times the molar mass. But we don't actually know the number of moles. We're only given the number of particles of helium atoms. So we have to use this formula here to determine the number of moles. Okay, so the number of moles is going to be equal to the number of particles, which is given to us in the question. It's 3.001, sorry, 3.011 by 10 to the 23 over Avogadro's number, okay, which is 6.022 by 10 to the 23. That's the number of moles, okay? And that's going to be exactly 0.5 if you calculate that in your calculators. And so we can just sub this into this formula here. So the mass is going to be 0.5 times the molar mass of helium. If you go to the periodic table on our formula sheets, it's the top right one on the periodic table. So it's going to be 4.03. 4.003. Okay. So the mass, if you calculate that in your calculators, is going to give us 2.0015 grams. Are there any questions on that? Okay, so we'll move on to this. So the molar mass, so the moles of a substance are related to its mass present, which can be divided by its molar mass to give us the moles present. So the term molar mass means the mass that is present in 1 mole, okay? So since moles are related to relative atomic mass, we can assume the atomic mass is equal to the molar mass of an element. Okay, so the relative atomic mass is equal to the molar mass of an element. Okay, so the formula for calculating moles, as we were using before, is the number of moles is equal to the mass divided by the molar mass, which we can see in this diagram here. Okay, so this triangle can help with our calculations, and it's important that you're consistent with your significant figures in mole calculations. Okay, so we'll go over some examples. So in this example, the molar mass of carbon dioxide is the molar mass of one carbon atom plus the molar mass of two oxygen atoms. So we use the molar mass of just one carbon atom, and we add it to two times the molar mass of one oxygen atom. And that's how we get the molar mass of carbon dioxide using the values in the periodic table. Okay, so that's how we will determine that for like molar calculations. So we'll move on to some examples. So we'll just do this one. I'll do part B. So part B, so then we asked what is the mass in 2.50 by 10 to the 4 moles of antimony tribromide. So antimony tribromide, so if it's going to be antimony tribromide, it's going to be Sb3 plus Br minus, as we're looking at before, and that's going to give us SbBr3. Okay, so we asked them for the mass. We have to calculate the mass. So given this formula that we're looking at before, the number of moles equal to the mass on the molar mass, we can manipulate this formula to find the mass. So we just multiply the number of moles times the molar mass. So we're given the number of moles, so that's great. But we have to calculate the molar mass of antimony tribromide. Okay, so the molar mass of antimony tribromide, we have to calculate ourselves. So it's going to be the molar mass of one antimony atom, which the periodic table tells us is 121.8, and then also we have to add that to 3 times the molar mass of bromine because there's 3 of them, 3 bromine molecules. So 3 times the molar mass of bromine is 79.9, and that's going to give us 361.5 grams per mole. So that's the molar mass. Okay, now we can sub this value into this formula. So the number of moles is equal to the mass. Oh, sorry, we're trying to find the mass, sorry. So the mass is equal to the number of moles, which is here. So 2.5 by 10 to the 4th over the molar mass. So that will give us, sorry, it's going to be multiplied what times? And that's going to give us a mass of, it's a really big number if you calculate it in your calculator. So it asks us for the mass in grams, so we just leave it in grams, okay? This formula gives us the mass is in grams for this formula, okay? So this is the final answer. So the mass of antimony tribromide in grams is going to be 9,037,500 grams, okay? So you can leave this as this many significant figures, but usually you would round it, okay? So when you're rounding to significant figures, you round it to the least number of significant figures given in the question. So since this is the only value we're given, and there's 2 significant figures, we round this value to 2 significant figures, okay? That's going to give us 9 million grams. That's our final answer. Are there any questions so far on that? Okay, we'll do just one more question. And then we'll stop because we don't have much time left. So we have the number of ions in 450 kilograms of barium hydroxide. We have to calculate the number of ions. Okay, so when we're trying to calculate the number of ions or atoms or molecules, we can just use this this equation, this formula, sorry. So the number of moles is equal to the particles over 6.022 by 10 to the 23. So that's going to be number of moles is equal to P on 6.022 by 10 to the 23. So the number of particles that we're trying to find is going to be the number of moles times Avogadro's constant. Okay, so now we have to determine how many moles are present so we can determine the number of ions. So the number of moles present in barium hydroxide would have to use the formula that we were using before. This is going to be the number of moles is equal to the mass over the molar mass. So the mass is going to be in grams. So we have to convert this 450 kilograms to grams. So we multiply it by 1,000 over the molar mass of barium hydroxide. Now the molar mass of barium hydroxide is going to be the molar mass of barium plus the molar mass of 2 oxygens and 2 hydrogens, all that added up. So that's going to be 137.3, I think that's for barium, and then 2 outside of 16, which is the molar mass of oxygen, I believe, and then of hydrogen. So we're multiplying 2 times the molar mass of oxygen, which is here, and then 2 times the molar mass of hydrogen, which is here. That's the total molar mass of barium hydroxide. Okay, so we put this value in this denominator here. So that's going to be, so if we calculate that in our calculators, we get the number of moles is equal to 2,626.724883. And so we have this value, and now we can use it in this formula, like how we intended to, okay? So the number of particles or the number of molecules of barium hydroxide is going to be the number of moles that we calculated here times, so I'm going to write that, so. And notice how I'm not rounding in my working out. So you try not to round in your working out. You only round in your final answer. So the number of moles times Avogadro's constant, so 6.022 by 10 to the 23. And so when we calculate that, we get 1.581813.724 by 10 to the 27 molecules of barium hydroxide. Okay, but we're not trying to find the molecules, the number of molecules of barium hydroxide. We're trying to find the number of ions in barium hydroxide. Now the number of ions in barium hydroxide, it's going to be the 1 barium and then the 2 hydroxide. Okay, because we have a subscript of 2 outside this hydroxide. So it's going to be 1 plus 2 ions. So we have to multiply this whole thing by 3 because there's 3 ions per barium hydroxide molecule. So that's why we multiply the number of particles by 3. And so the number, this gives us 4.745441173 by 10 to the 27 ions. Now, you should write your unrounded answer first, and then in your final statement, write down the rounded answer. So therefore, the number of ions, so you should always have a final statement, number of ions in 450 kilograms of barium hydroxide is, and we round this to 2 significant figures, okay? Because this value is in 2 significant figures, to 2 significant figures. So this to 2 significant figures is going to be 4.7 by 10 to the 27 ions, okay? Yeah. And that's, we have to write 2SF because when you round, you have to actually state how many ions. So that's our final answer. Are there any questions so far? Just put it into the chat. So like we're basically done now because we're running out of time. So if there's any questions, just pop it into the chat and I'll answer them. Okay. Well, that was the whole chemistry crash course for today. So thank you so much, everyone, for joining, and I hope that this was good. And yeah, thank you. No worries, everyone. Thank you so much. Okay, I'll be ending the meeting now. But like everyone's left already, so sorry.
This will be the end of the recording. So end the call now.